Okay guys, welcome to GR Hub Mathematics and Statistics lessons. In today's class, I'm going to be talking about indices, the laws of indices. So, I'm going to start with the definition of indices. So quickly, let's begin with the definition of indices. So, the first question is, what is indices? So if you're taking indices as a topic in the course General Mathematics 1 or Algebra and Trigonometry, please take note that indices is a branch or topic in mathematics. So it is a topic in mathematics that discusses the laws governing an index number and the application. So, you must be able to tell someone what indices is all about. So in today's class, we will be studying indices, and it is best we start with the definition of indices. So let's go over it again. What is indices? Indices is a branch or topic in mathematics that does what? That discusses the laws governing what we call index numbers and their applications. Now please take note that there are variations to this definition, so the definition can be flexible provided it talks about the essential thing about indices. So indices is a branch of mathematics or a topic in mathematics that discusses the laws governing index numbers and their applications. So that being said, now that we know what indices is, let us now go to the next thing I want you to understand. Now these things will guide us to what we shall be discussing proper, which is the laws of indices. So the next thing I want you to know is index notation. Index notation. So when is a number said to be in index notation or index form? So it's either you call it the index notation of a number or the index form of a number. So that is what I want us to discuss next. So again, we are discussing the laws of indices, and we have started our discussion with the definition of indices, which tells us that indices can be considered a branch of mathematics or a topic in mathematics that does what? That discusses the laws governing index numbers and their applications. So, when a number is called an index number or said to be in index form or index notation, how do we represent such numbers? So let's consider a number, say 25, before taking a definition or a description on this. Let's consider a number, say 25. Now, I could use the letter Y to represent 25. So let's say 25 is represented with Y. Now, what can we say is the index notation or the index form of 25? 25 can be written as 5 raised to the power of 2. Okay? 25 can be written as 5 raised to the power of 2, which means 5 multiplying itself 2 times. So, this form of writing 25 or expressing 25 is said to be the index notation or index form of 25. So, let's use a number A, a letter A, to represent 5, and let's use another letter X to represent 2. You would come to realize that the index form of a number, say y, is an expression a raised to the power of x. So I could even change this to m, and this will become y equals a raised to the power n. So when it is possible to express a number, say y, in the form a raised to the power m, this form of writing the number y is said to be the index notation of y, or the index form of y. Now please take note, if you want to now explain what is the index notation or index form of a number, so I'm going to say this: the index form of a number y is the expression a raised to the power x, where a is called the base, and x may be called 1. You could call x power. 2. You could call x index. 3. You could call x exponent. Okay? So, what is the index form of a number? If we take a number y and want to express that number y in index form, what it means is to write y in the form a to the power of m. So let me change this to m to be consistent. So what it means to write y in its index form means writing y as a raised to the power m, such that this a here is called the base, the m is called either of any of these three names. Power, this a could be called power, this m could be called power, the m could be called index, or the m could be called exponent. Subsequently, in my next class, you will come to realize that this m could also be called logarithm. So there are basically four names you could call m. If y can be expressed as a raised to the power m, where a is the base, then m could be called power, it could be called index, it could be called exponent, and it could even be called logarithm. Okay? So that explains the description on index notation or index form. Now let's take an example, or let's take several examples on index form. So what is the index form, I repeat, of 25? It is 5 raised to power 2, implying that in this case, in the index form of 25, 5 is the base and 2 is the power. What about the index form of 64? You will come to realize that 64 can be expressed as 8 raised to the power of 2. And in this case, when 64 is expressed as 8 raised to the power 2, you will notice that our base is 8 and our power is 2. Now, there is something I'm going to explain before we proceed. It answers this question. Can a number have more than one index form? Can a number have more than one index form? So, if you are asking this kind of question, the answer is a big yes. One number can have more than one index form. Now, let me show you. One number can have more than one index form. So I'm going to wipe this off quickly so that we could actually see what is being explained here. So one number can have more than one index form. What it means is this. Let's go back to the example of 64. So 64 can be written as 8 raised to the power of 2, implying that 8 raised to the power of 2 is the index form of 64. In which instance, 8 is the base and 2 is the power. Take note, 2, if you don't want to call it power, you could call it index. If you don't want to call it index, you could call it exponent. If you don't want to call it exponent, you could call it logarithm. But let's save that for a later discussion. Now, another way to write 64 may be 4 raised to the power of 3. 64 could also be written or expressed in index form as 4 raised to the power of 3. So this is one number, 64, having 8 raised to the power of 2 as its index form and having 4 raised to the power of 3 as another index form. So when 64 is expressed in index form as 4 raised to the power of 3, what is the base, guys? You guessed right. The base is 4, and what is the power in this instance? It is 3. Take note again, the same 64 can be expressed as 2 raised to the power 6. Now, 2 raised to the power 6 is another index form of 64. And that implies that in this instance, the base is 2 and the power is 6. So, this answers the question that one number can have more than one index form. Now, you could look at more examples on that with 625, which could be expressed as 5 raised to the power 4, which could also be expressed as 25 raised to the power 2. So these are instances of numbers having more than one index form. So what again is the index form of a number? It is an expression having a base and a power, which could also be called index, exponent, or logarithm, as you would see subsequently. Now, that being said, let us now expatiate on the index form. Let's expatiate on the index form of a number. What more is there to say about the index form of a number, guys? The next thing I want to say about the index form of a number is this. So let's look at this again. 25 being 5 raised to the power 2. 25 expressed in index form as 5 raised to the power 2 implies that the power here tells the number of times the base will multiply its own self. So if you have 5 raised to the power 2 as the index form of 25, this means that 5 would multiply itself 2 times to get 25. So if you end up having 64 expressed as 2 raised to the power 6, it means that 2 raised to the power 6 means to get 64 using 2 as the base, then 2 would have to multiply itself 6 times. So what does it mean, guys? The power, the index, the exponent, also known as the logarithm, defines the number of times the base in an index form must multiply itself to give the number expressed in index form. So if 2 raised to the power 6 is the index form of 64, it simply means that to get 64, 2, the base, must multiply itself 6 times to produce 64. And of course, you will see that 2 raised to the power 3 is 8, and 2 raised to the power 3 is 8. 8 times 8, of course, will give you 64. So that is another thing to note, guys, that when numbers are expressed in index form, it simply can be expanded in this manner. Now, we are going to be using a notation in my lesson with you guys on the laws of indices. Let's go back to the generalization I put earlier on. So, if 64 can be expressed as 2 raised to the power 6 and can be expanded in this manner, and 25 can be expressed as 5 raised to the power 2 in index form and expanded in this manner, how then would we be expanding this? What then does this mean? When we write y equals a raised to the power n as the index form of y, how can we expand it? In my lesson with you guys, the expansion would mean a multiplying itself m number of times. So we are going to be using this notation. So this is what I'm going to do. To show that a is multiplying itself m number of times, I'm going to do this. I'm going to be using this. So I'm going to put underneath this m times. So y equals a raised to the power n simply means that the base a is multiplying itself m number of times. So please take note of this notation it will help us improving the laws of indices. So that being said, now that we have talked about the definition of indices, now that we have described index form of a number, now that we've also talked about two key points on the index form of a number, being the uniqueness or non-uniqueness of the index form of a number and the expansion of index forms of numbers, let us now go into the laws of indices. Guys, there are 10 laws of indices, and we are going to first of all mention all of them. So let's mention all the laws of indices. Let's mention quickly the laws of indices. So let's start with mentioning the laws of indices. So laws of indices. Number one, the first law we are going to be looking at under the laws of indices is called the addition law. The addition law. So what does this law state? It states that when two numbers are in the index, when the index form of two numbers are multiplied such that the bases are the same, then the result is the same as one base raised to the sum or the addition of the respective powers. So again, take a look at it. Let's assume I have a raised to power m as the index form of this number y, and I have a raised to power n as the index form of this number z. So multiplying y with z can be simplified using this expression a raised to power m plus n. That is, provided this law will only hold when the bases are the same. Take note, a is the base here and a is the base. So if it is possible to write y, this number, in an index form such that the base is a, having a raised to power m, and you can also subject z to be written in index form as a raised to power n, the same base as the index form of this, then the result will be a raised to power m plus n. So this law is called the addition law. Now the next law we are going to be looking at, is the subtraction law. Law number 2 is the subtraction law. The subtraction law. So this law is similar to this law, only that in this case we are not multiplying. When two numbers in index form are divided one by another, the result is the base in their index forms raised to the subtraction of one power from the other. So you end up having a raised to power m divided by a raised to power n is equal to a raised to power m minus n. So this law is the second law, and it is called the subtraction law. Let's go to law number 3. Law number 3 simply says a raised to power 0, if there is a base raised to the power of 0, the result will give you 1. Okay? Then law number 4 comes in as a raised to power 1 is a. Okay? Then comes law number 5. Law number 5, of course, you can call this law the law of zero power. You can call this law the law of zero power. You can call this law the law of unity. Then comes another law, the law of powers of power. Power of power, or the law of exponent. So in this law, when a base is raised to a power, when a number in index form is raised to another power, so that you have a raised to power m representing the index form of another number, and that number is raised to another power n, the result is the same as a raised to power mn, the powers multiplying themselves. Okay? So I'm going to take examples on this law. Let's go to law number 6. Let's go to law number 6. So I told you that there are 10 laws. Let's go to law number 6. So in law number 1 we have the addition law. Law number 2 we have the subtraction law. Law number 3 we have the zero power law. Law number 4 we have the unity law. Law number 5 we have the power of power. Then law number 6 is called the law of negative index. So a raised to power minus n is 1 over a raised to power n. So this law is called the law of negative index, and that is law number 6. the law of negative index, telling you that when a base is raised to a negative power, the result is the same as 1 all over the base raised to the positive power. Okay? Now let's go to law number 7. In law number 7, we have the law of shared powers, and this law has two variations. So I'm going to separate them, calling them law number 7 and 8. So in law number 7, we have AB raised to power m is the same as A raised to power m times B raised to power n. Now, in this law, please take note. When two different numbers, two different bases, have in product have the same power, the result is the same as the first carrying that power multiplying the second carrying that power. So A times B raised to power m is equal to A raised to power m times B raised to power n. Now, this is one variation of this law, the law of shared power. Now, let's look at the second variation, A over B raised to power n. In the first variation, you will notice that the two bases were multiplied. In the second variation, they are divided one by another. So A over B raised to power m is A raised to power m divided by B raised to power n. So these two laws, if you are studying General Mathematics 1 and the topic you are dealing with in your respective schools or colleges is currently indices, please take note that these two laws together are called the law of shared power. So I'm going to call them law of shared power. Now, I often would explain this to my students as the law governing your surname. You will notice that if there is a child, if there are two children in a particular home, you will notice that this may answer John, this may answer Olive. Notice that John and Olive have something in common. What they have in common is M, their surname. So if the surname is Michael, then one child will answer John Michael and the other will answer Olive Michael. So I often would use that example to explain these laws to students. So please take note, these two laws are called the laws of shared power. Now let's go to law number 9 and 10. Law number 9 and law number 10 are variations of one another. So let's look at those laws. What does the law say? A raised to power 1 over n, or let's use 1 over m to be consistent. A raised to the power 1 over m is equal to the mth root of a. So what do we call this law? This law is called the law of fractional index. So there are two variations to the law of fractional index. This law number 9, is called the law of fractional index. Now, you will notice that in law number 9, in this fraction, the base here carries a fraction 1 over n. And the numerator of the fraction in law number 9 is 1. Now, take note, in law number 10, whereas in law number 9, the numerator is 1, in law number 10, the numerator is, okay, I'm going to use this. Let's go with n so that it makes more sense and it makes more meaning as we proceed. So notice that this is a raised to power 1 over n, giving us the nth root of a. Now, the second variation of this law says that a raised to power m over n is equal to the nth root of a all raised to power m. So these are the 10 laws of indices. Okay, these are the 10 laws of indices. Now, that being said, let's go over them again quickly and then go to the proof of these laws. Law number 1 is the addition law. Law number 2 is the subtraction law. Law number 3 is the zero power law. Law number 4 is the unity law. Law number 5 is the power of power law. Law number 6 is the law of negative index. Law number 7 and law number 8 both are called the law of shared power. Law number 9 and law number 10 are both called the laws of negative index. The laws of negative index. Good. Now, that being said, let us now take quick examples on these laws. I'm going to show you quickly some examples on these laws, and we shall go to the end of my class, in which case I'm going to be proving the laws. So let's take examples first on each of these laws. How do you use these laws to solve problems. Okay, so let's start with the power law. Let's assume you were given a problem like this. You were asked to solve the problem. Solve the problem. Let's take an example on the addition law. So solve the problem 3 raised to power 6 times 3 raised to power 2. So this kind of problem is solved by the addition law. Notice that there is a resemblance between this problem and the addition law because the bases must be the same. So take note, this cannot be solved with the addition law. Simply because if you have 3 raised to power 6 multiplying 4 raised to power 2, the bases are not the same. So it will be wrong of you to say that this is 3 raised to power 6 plus 2 or this is 4 raised to power 6 plus 2. You will be very wrong. So for you to apply the addition law to a problem like this, then the bases must have been the same. Now, if the bases are the same, 3 raised to power 6 times 3 raised to power 2 would end up giving you 3 raised to power 6 plus 2, which is 3 raised to power 8, and that solves the problem. So when you use the addition law, you use the addition law under cases like this. Please take note, after my class on indices, I'm going to be dropping a video, another video in which I'll be solving problems on indices. So it will be a solver series on indices where we shall be looking at so many problems to be solved using all of these laws combined, or all of them, some of them combined, okay? So now for the second law being the subtraction law, what if the problem was to solve 3 raised to power 6 divided by 3 raised to power 2? The subtraction law will come in this case. In which case, all you have to do according to the subtraction law, provided the bases are the same, then you subtract the second power from the first power, meaning that your answer in this case will be 3 raised to power 6 minus 2, which is 3 raised to power 4. Okay? Now, what if you were asked to solve a problem like this, 100 raised to the power of 0? Please take note, according to law number 3, anything raised to the power of 0 returns 1. So 100 raised to power 0 is 1, 25 raised to power 0 is 1, 60 raised to power 0 is 1, and so on. So if I have z raised to power 0, anything at all raised to power 0 according to law number 3 gives us 1. And that brings me to law number 4. So what kind of problems do you find in law number 4? What if you were given the problem 25 raised to power 1? What is 25 raised to power 1? Any number raised to the power of 1 is the number itself. So 25 raised to power 1 is 25. What if I gave you a problem like this? 5 raised to power 3 minus 2. 5 raised to power 3 minus 2 would give you 5 raised to power 1, which ends up giving you 5, because 5 raised to power 1 according to that law is 5. Now, then comes law number 5. Law number 5, when does it set in? What if I gave you the problem to solve 3 raised to power 6 raised to power 2? Notice that 3 raised to power 6 is the index form of a certain number. Now, raising it again to the power of 2 simply means that you are going to have 3 raised to power 6 times 2 according to that law, and that gives you 3 raised to power 12. So if you raise 3 raised to power 6 to 2, another power, your result will be the same as 3 raised to power, the product of the powers, which is 3 raised to power 6 times 2, giving you 3 raised to power 12. Now, let's go over to an example on law number 6. Let's go to an example on law number 6. So, as an example on law number 6, look at an example on law number 6, the law of negative index. So, this law is used for solving problems like this. So, you end up having 3 raised to power 2 minus 6. If you were to solve 3 raised to power 2 minus 6, take note, 3 raised to power 2 minus 6 will return 3 raised to power 1 over 4. Okay? 3 raised to power minus 4. And when it comes to this level, it means you can use that law to simplify, and it will give you 3 raised to power 1 over 3 raised to power 4. So you use that law of negative index to simplify a problem such as this. So what is 5 raised to power minus 3, guys? It will be 1 over 5 raised to power 3, which will end up giving you 1 over 125, because 5 raised to power 3 is 125. Now, for problem number 7, problem number 7 comes in this manner. I can use the laws in 7 and 8 to solve problems of this kind. So what if I was given 3 raised to power 6 times 5 raised to power 6? Now notice that two different bases having the same power. I could simplify this problem to say 3 times 5 raised to power 6. Why do I have the audacity to do this? I am justified by law number 7. So law number 7 gives me the audacity to do this, because when two or more bases are different but carrying the same power in multiplication, then you can multiply the two bases raised to the same power. So that would end up giving me 15 raised to power 6. And that's an application of law number 7. So for law number 8, what if this problem were not to be in multiplication, it was rather in division? That is, you had this 3 raised to power 6 divided by 5 raised to power 6. Of course, by law number 8, this problem can be solved by doing this 3 over 5 raised to power 6. Why do you have the audacity to do this? It is because according to the law 8 here, a over b raised to power m is a raised to power m divided by b raised to the power of m. Okay, so these are cases where you apply laws number 7 and 8. What about law number 9 and law number 10? So in this instance, I'm going to explain this further, but take note. What if you were asked to simplify this? 25 raised to power 1 over 2. And this is where I have to give a little explanation. Please take note. You will notice that a raised to power 1 over n, according to law number 9, is the nth root of a. Please take note. You do not, it will be wrong of you to write 2, 25. It will be wrong of you to express this as this. When the denominator is 2, by convention, you don't write the 2. But for numbers greater than 2, every number greater than 2, you can write. So for values of n, provided n is greater than 2, when n is greater than 2, you can indicate. Okay? But when n is 2, you do not put 2 here. So I'm going to remove my 2 by convention, and that means 25 raised to power half. The index here is fractional. 25 raised to power half, take note, the power has the numerator as 1. So 25 raised to power half will be the square root of 25, and that gives me my result as 5. Okay? Why? The square root of a number is that one number that would multiply itself twice to give that number producing the square root. Okay? So looking at this, what if I had 64 raised to power 1 over 3? 64 raised to power 1 over 3 looks like law number 9. So I'm going to have the cube root of 64. And what is the cube root of 64? It is that one number that will multiply itself 3 times to give 64. And the only number that will multiply itself 3 times to give 64, guys, is 4. So 4 is the cube root of 64. Why? 4 times 4 is 16. 16 times 4, another 4, the third 4 will give you 64. Okay? Now, what if you had 64 raised to power 1 over 6? What if you had this? Then this would mean the 6th root of 64. What is the 6th root of 64, guys? It is 2. Okay? Because 2 is the only number that will multiply itself 6 times to give 64. So these are problems that can be solved with law number 9. Let us now look at law number 10. Let us look at law number 10. So for law number 10, quickly, let's look at variations to that problem now. So for this, what if we had 25 raised to power 3 over 2? The result will be the square root of 25 all raised to the power of 3. And that would have given us 5 raised to power 3, which is 15, according to law number 10. Law number 10 talks about a case where the numerator in the index, the fractional index, is not 1. So it is m in this case. Now, look at law number 10. It says that a raised to power m over n is the nth root of a all raised to power n. And that gives me 25 raised to power 3 over 2 as the square root of 25 raised to power 3. And the square root of 25 is what? It is 5. 5 raised to power 3. 5 raised to power 3 will give me 125. That was an error. Sorry, guys. So, let's go over to the next. Sorry for that mistake. So, let's go to 64 raised to power, let's say, in this case, 2 over 3. 64 raised to power 2 over 3 will give you the cube root of 64 all raised to power 2. And what is the cube root of 64? We got the cube root of 64 as 4. So this will give you 4 raised to power 2, and 4 raised to power 2 is 16. Now, what about 64 raised to power, let's say 5 over 6? 64 raised to power 5 over 6 will give you the 6th root of 64, which is, of course, 2 raised to power 5. And that would mean the 6th root of 64, which is 2 raised to power 5, gives us 32. So these are problems that can be solved using law number 10. Okay? So what have we done so far, guys? In this class or this lesson on indices, the laws of indices, we have defined indices. If you are taking a course on indices or a topic indices in a course general mathematics 1 or algebra and trigonometry, as the case may be, please take note. You must start with knowing what indices as a topic is all about, followed by knowing what index notation or index form means. And we have explained that in this video. What the law or what indices is defined to be, what index notation or index form of a number is, and what remarks can be made on the uniqueness or non-uniqueness of the index form of a number and the expanded form of the index form of a number. Okay, so at present we have just looked at the laws of indices and examples on the laws of indices. I'm going to end this class with proving the laws of indices. So please take note, watch out for the next video on indices. The next video on indices, this is my class on indices where I have taught you basic things you need to know about indices. In that next video on indices, I will be solving problems only on indices. So please watch out for that video, like this video, share this video, and subscribe to the YouTube channel GER Hub. It is a place to be. So let's go to the laws of indices, proving the laws of indices quickly. So I'm going to prove the laws of indices in the order at best that I had arranged them. I'm going to prove the laws of indices. So let's look at proving the laws of indices, guys. So please do well to like this video, smash the like button whenever you get to watch this video. If you're not watching it live but will be watching it later, do well to subscribe to the channel. Click the subscription button. Please support the channel by giving us your free subscription. Subscribe to the channel, smash a like on the video, share the video, tell guys about GER Hub. It is a place to be where we teach mathematics content, statistics content, and of course research content. So please, it is a place to be. Now let's prove the laws of indices. So I'm going to start with the addition law. So proving the laws of indices. Proving the laws of indices. Okay? So just in case you do not know how to prove the laws of indices, let's start with this. The first law is a raised to power m times a raised to power n equals a raised to power m plus n. I'm going to be using, note that this is the left hand side and this is the right hand side. So I'm going to be using a one-sided proof. I'm going to be proving from this side, the left hand side, to the right hand side. So please take note. Now this is what I'm going to do. A raised to power m times a raised to power n. Remember, I had told you earlier on that a raised to power m means multiplying a by itself. How many times? M times. So I'm going to write this in expanded notation. Okay? So a raised to power m means multiplying a by itself n times. I'm going to use a bigger multiplication sign different from this smaller multiplication signs to show the difference between this and this. So, on the other hand, a raised to power n is multiplying a by itself n times. N times. So, if you multiply, take note, there is no difference between this big multiplication sign and this smaller multiplication sign. I'm only using it to show you the separation. Okay? So, if a is multiplying itself n times to give a raised to power n, and the same a is multiplying itself n times to give a raised to power n, if you put all the a's together in multiplication, it will mean that if you put all the a's together, you end up having a multiplying itself a total of m plus n times. Okay? So if a multiplies a raised to the power m can be written as a multiplying itself n times, and a raised to the power n can be written as a multiplying itself n times. Mixing all the a's together in multiplication will produce a total of m plus n a's in multiplication, and that can be written in index notation as a raised to the power m plus n, and that completes the law. So it is simple to prove the addition law. To prove the addition law entails using this expanded notation and simple logic, and it proves the addition law. Now, what about the subtraction law? What about the subtraction law? So for the subtraction law, we have a raised to the power m divided by a raised to the power n. We are going to be using similar logic. So the subtraction law states this, okay? So what are we going to do? We are going to write a raised to the power m divided by a raised to the power n in this manner. Now, this is a raised to the power n. I'm going to write it as a times a times a times a total of m times, divided by a times a times a times ellipsis a total of n times. Now, please take note, this law of subtraction works under the assumption that m is greater than n, invariably implying that n is less than n. Okay? So, look at it this way. If you are proving this law, please take note. We are assuming that the number of a's, the m a's, are more than the n a's. Now, look at it this way. If m a's above in the numerator are more than n a's, it means that after cancelling, if you cancel out n a's from the m a's, you will be left with a total of a times ellipsis a m minus n a's left, and that would mean writing it as a raised to the power m minus n. Let me give you an example of this. This is what I mean. So let's assume that you have a raised to the power 3, a raised to the power 5 divided by a raised to the power 2. So in this case, your m is 5 and your 2 is n. Notice that provided 5, your m, is greater than 2, your n, then a times a times a times a, 5 a's above, will be cancelled out completely by 2 a's below. And if 2 a's below cancel out 2 a's, corresponding 2 a's above, you will be left with 3 a's above. And these 3 a's correspond to 5 minus 2. Okay? So that proves the second law, the subtraction law of indices. Now let's go to the third law. The third law I mentioned earlier was a raised to the power 0 equals 1. How do you prove this law, guys? To prove this law, all you have to do is to use this simple logic. Start with writing a raised to the power 0 as a raised to the power a number minus itself. To get 0, a number should be subtracted from its own self. So instead of writing 0, I'm going to write m minus m. And a raised to the power m minus m happens to be the right hand side of the subtraction law. And notice that writing it out in the left hand side of the subtraction law, a raised to the power m minus m can be written as a raised to the power m all over a raised to the power m. That is, it can be written as a raised to the power m divided by a raised to the power n, which can be written as this in your own understanding, and this cancels this to give 1. So a raised to the power 0 is always 1, simply because a raised to the power 0 means a raised to the power a number subtracted from itself, giving you a raised to the power m divided by a raised to the power m by the subtraction law, and when it cancels, you get 1. Now, let's come over to law number 4, a raised to the power 1. Why is a raised to the power 1 a? Now, the best way to explain this is using the subtraction law again. How would you do this? A raised to the power 1 can be written as a raised to the power m, a raised to the power m minus, in bracket, m minus 1. Okay? So, notice that if I subtract, if m is 5, for instance, then m minus 1 will be 1 short of 5, which is 4. So one way to write a raised to the power 1 is like saying a raised to the power 5 minus 4, a raised to the power 6 minus 5, a raised to the power 3 minus 2, which is the same algebraically as writing a raised to the power 1 as a raised to the power m minus in bracket m minus 1. Okay? And that will give you this, a raised to the power m divided by a raised to the power m minus 1. So this means that if there are MA's in the numerator, and there are m minus 1 a's in the denominator, so if you have m minus 1 a's in the denominator and you have m a's in the numerator, notice that because m is greater than m minus 1 by 1, m minus 1 a's will cancel out all the m minus 1 a's in the numerator and you'll be left with just 1a. So a raised to the power 1 is a. Now, that brings me to law number 5. How do we prove law number 5? How do we prove law number 5? So to prove law number 5 was on powers of power. So to prove law number 5, I could have a raised to the power m raised to the power n equals a raised to the power mn. Why is this so? A raised to the power m raised to the power n is the same as saying a raised to the power m times a raised to the power m times a raised to the power m times ellipsis times a raised to the power n. That is multiplying a raised to the power m, which is in bracket n times. And that means by indices, by the addition law of indices, this will be m plus m plus m. All the powers, since they are the same base, the powers will add up. How many times? The powers will add up n number of times. And when you add a certain constant, a fixed number of times. So if I add 5 3 times, adding 5 3 times is the same thing as 3 times 5. So adding n times is the same thing as mn. So that proves this law. A raised to the power m in bracket n is the same as a raised to the power mn. So when a number in index form is raised to another power, the two powers will multiply themselves, and that is the proof of that law. So let's go to law number 6. Let's go to law number 6. What was law number 6, guys? Law number 6 was the law of negative index. So a raised to the power m, a raised to the power minus n is 1 over a raised to the power n. Okay? So how do you prove this law? We start by writing this. A raised to the power n minus n can be written as, I could write a raised to the power minus n as a raised to the power 0 minus n. So I've done nothing wrong. A raised to the power minus n can be written as a raised to the power 0 minus n. And according to the subtraction law, this can now be written as a raised to the power 0 divided by a raised to the power m. Okay? According to the subtraction law. And this means 1, because a raised to the power 0 according to the 0 law is 0 power law is 1. So this will be 1 divided by a raised to the power n, which can be written as 1 over a raised to the power n. And that proves this law to be true. So law number 6 is true. If you want to prove law number 6 again, a raised to the power minus m is 1 over a raised to the power n. That's the law. To prove it, all you have to do is write a raised to the power minus m as a raised to the power 0 minus m. Of course, 0 minus anything will give you that thing. So 0 minus m will give you minus m. So we've done nothing wrong here. So a raised to the power 0 minus m can be expressed in the subtraction law as a raised to the power 0 divided by a raised to the power m. So that's what I've done here. But according to the 0 power law we have stated earlier and proved earlier, a raised to the power 0 is 1. So if we replace this with 1, then it now implies 1 a raised to the power 0 divided by a raised to the power m is 1 divided by a raised to the power m, and that gives you 1 over a raised to the power n. And that proves law number 6. So let's go to law number 7. How do we prove law number 7, guys? To prove law number 7 and law number 8, Remember, law number 7 and law number 8 are the laws of shared power. So let's start with law number 7. So we had AB raised to power m is A raised to power m, B raised to power n. This was law number 7. So how do we prove this? To prove this, all I'm going to do is AB raised to power m will be written in expanded form as AB raised to power AB times AB times AB times AB. How many times? How many times are we multiplying AB? Of course, we are multiplying AB by itself m times. Now, you could call it taking like terms. Separate A. Note that AB is the same thing as A times B. So I'm going to gather all the A's in multiplication. Of course, because I have them m times, I'm going to have A in multiplication m times B in multiplication. When you separate, you are going to have B in multiplication m times also. Okay? Now, if you express this in index form, this will be A raised to power m. If you express this in index form, this will be B raised to power m, which can be written as A raised to power m, B raised to power n. And that proves law number 7. Now let's come over to law number 8. A similar logic follows for law number 8. A over B raised to power m is equal to A raised to power mb over B raised to power n. So how do we prove this? We follow a similar logic. A over B raised to power m can be written as A over B times A over B times A over B times Indices times A over B. And that will multiply how many times? M times. That will multiply n times. Now let's come over here to continue that problem. So let's continue over here. So to get that done, what do we now do? You can now go on to gather all the A's in the numerator. Of course, there will be a total of m A's in the numerator. So m times A multiplying itself, and there will be a total of m B's in the denominator m times. Okay? So this would end up giving you A raised to power m all over B raised to power n. And that proves that law number 8. Now, let's move over to law number 9. Law number 9 and law number 10, I told you, are the laws of fractional index. So the first variant of the law of fractional index is law number 9, which states that A raised to power 1 over n is equal to the nth root of A. Now, to prove this law, we use the inductive proof. Okay? So it's not like this proof we've done previously. All you have to do is just to use the law of induction. So, not necessarily the law of induction, but just infer using induction. So, A raised to power 1 over 2 can be written as the square root of A. A raised to power 1 over 3 can be written as the cube root of A. A raised to power 1 over 4 can be written as the fourth root of A. And it goes on, we can infer that A raised to power n can be written as the nth root of A. Bearing in mind that, please take note, A raised to power half, by definition, is the number. When you raise A to the power of half, it simply means you are referring to a result that will multiply itself 2 times to give A. So A raised to power half, going by that, is the square root of A. And A raised to power 1 over 3 is the cube root of A, simply because you are referring to a result whose multiplication of itself 3 times will give A. And that is what we refer to as the cube root of A. The fourth root of A will be a number that will multiply itself 4 times to give A. And that will continue up to the point of A raised to power 1 over n. A raised to power 1 over n will be a number that will multiply itself n times to give the result A. So by induction, you would have that. And let's now go over to 10. Why is 10 true? 10 is true because 9 is true. So if you want to prove that a raised to power m over n is the nth root of a all raised to power n, all you have to do is to use the law number 5, which was the power of power law. So I'm going to do this. I can write this as this. I can write a raised to power m over n in this manner. So I can write a raised to power m over n, separating it as a raised to power 1 over n all raised to power n. And that would mean having a raised to power 1 over n, which is the nth root of a all raised to the power of n. That's one way to go about it. You can go about it in some other way different from this, but these laws are just simply inferred from what you have here. The proof of this law is inferred from what you have here. Okay? So that being said, please go over my video from start to finish. It was a nice time having you guys watching this video on the laws of indices. A quick recap over what we've done. We started this class with discussing the very first thing. In this video, we have defined indices. So we started our class with defining indices, where we answered the question, what is indices? We went on from this point to the next point, explaining the index form. We explained the index form or index notation of a number. So we answered the question, what is the index form of a number? Now, the next thing we did was to explain the uniqueness or non-uniqueness of index form. So we answered the question, can one number have more than one index form? We have answered this question in this video. The next thing we did was to give the expanded notation for the index form. Expanded notation for index forms. We have dealt with that in this video. Then the next thing we went on to discuss was the laws of indices. So under the laws of indices, guys, in this video, we have stated the laws of indices and we have proved the laws of indices. Please subscribe to the channel GERO. More videos will be uploaded. More videos will be uploaded when we go live, of course. So please do well to watch the videos we've uploaded on our channel. This video was a video on indices. Like the videos, share the videos to your friends, and subscribe to the channel. Smash a like on this video, and I'll be seeing you in my next video where I shall be solving problems on indices. Until then, Happy New Year. God bless you.